That's correct. Thank you. I want to start off by thanking the organizers for giving me the opportunity to speak at this conference. And with this, I would like to introduce the topic of my talk, so scaling up Pichia Pastoris processes. Next slide, please. So we have had a lot of interesting talks already about strain engineering and fermentation optimization. We at the Biobase Zero pilot plant, we're mainly focusing on scale up, and we do this both on the upstream and the downstream part. So for this talk, I will focus mainly on the downstream part of the recombinant protein production process. So I don't think I have to explain this centrifuge. I think most of you will be familiar with this type of machine. But of course, this is what happens on lab scale, on an industrial scale. There are different volumes. I think you can process still volumes of lab fermenters up to 10, maybe even 20 liters. But after that, you would need very motivated technicians or very motivated students to separate your biomass from your supernatant and this type of machines. So on industrial scale, and then you can press next, we have a lot of different units that are available for biomass separation. And this is what I want to explain during my talk. So you can go next. So as a case study, we have a collaboration project at the end of last year. It was a short but intense collaboration project together with Pichia, so the group of Tony Glieder and the University of Barcelona together with Xavi. And there we looked into how we can efficiently recover the UPO12, so unspecific peroxygenase, and how we can remove biomass in an efficient but also scalable way. And for this, we have looked into three different strategies. So there are three that are the most obvious and most commonly used for biomass removal, and I've listed them there. So we started with evaluating ceramic cross-flow microfiltration, so also known as tangential filtration. And then we also looked into filter press, dead-end filtration, and distech centrifugation. So you can go next. So for ceramic microfiltration, we have tried to remove our biomass with ceramic membranes. So they have a size of about 0.45 micrometers, which should effectively remove all biomass. The size is approximately 450 kilodalton as well. And what I want to highlight here is that the UPO enzyme with glycosylations is about 55 kilodaltons. So looking at this, you would expect that UPO12 would easily go through the membranes, but in our first screening experiment, which you can see on the next slide, so here you can see the rejection of UPO12 by these membranes. And very interestingly, we saw that there was a very high rejection. Of course, we don't want high rejection because we want a high recovery. And even at different pH values, different transmembrane pressures, which is the pressure that you can apply during your filtration step. So, of course, enzymes and proteins and the extension are very complicated molecules, so they can interact with these ceramic membranes, and that can partially explain what we see here. We do see that the best results were obtained at the isoelectric point, so at a pH of 5.1 of the UPO12 enzyme. So, not completely discouraged by these results, we wanted to further evaluate what the effect was of prolonged biomass removal, so prolonged filtration, and to see what this did to the recovery. And you can go to the next slide. So what we saw there is that membrane fouling, which is a commonly observed struggle in filtration processes, is after even only 30 minutes of recirculation, we saw immediately that the rejection for all pH values at our best condition of the transmembrane pressure jumped up to almost 90 98%. And this can be caused, for example, by the use of anti-foam. So here I would like to highlight as well the importance of the close collaboration between both upstream and downstream sections. And of course, protein binding to ceramic membranes can also cause this, low recovery. Following these results, we decided to move on to another biomass removal strategy, and this was filter press filtration. At Biobasure pilot plant, we have a small-scale filter press available that allows us to quickly, with small volumes, test this unit in a very representative setting that is easily scalable to larger volumes. What I want to highlight here is that the clarification of the supernatant is partially achieved, but further polishing is still necessary. And then I think on the pictures on the next slide, you can see that we obtained a very nice cake when opening the chambers of the chamber filter press. And you can see on the falcons, the left one is before treatment, so it's just the broth immediately from the fermentation. And the second one is then the supernatant that has been partially clarified. But if you zoom in on if you go to the next slide. So zooming in, I think it's a bit difficult to see from far away, but you can still see that there's a very little pellet still present in the supernatant, which will have to be removed later on in the process. So, happy with these results, we decided to validate these results on pilot scale. So for that we ran a 150 liter fermentation process. And then you can go to the next slide. We designed the process to be run at pilot scale, so both fermentation as well as the DSP. And then one next slide. And for this we used this chamber filter press, which is capable of handling volumes of at least 150 liter. And they are very representative and easily scalable to bigger volumes as well. The results that we got there were very encouraging. So initially we got 86% of UPO12 recovery. And after an additional biomass washing, we were able to increase this to more than 95%. So this is very important, especially for industrial enzymes, because you want to have a cost price as low as possible. So evidently you want to have an as high as possible recovery. What I want to highlight here as well is that we have dry matter of the cakes of more than 30%. So you can achieve very dry cakes with this strategy. Another thing that I want to mention here is that we had to use filter rates for this to achieve these results. And what's important to know is with filter rates, you bring foreign particles into your biomass, which can be not as desirable, especially if you focus, for example, on biomass valorization, which I think there was also a poster here, where we really try to focus on the valorization of, let's say, waste streams, such as the Pichia biomass. Looking into the following strategy, we evaluated distech centrifugation. A huge benefit of this strategy compared to chamber filter press filtration is that this can be operated in a very continuous manner. Where you are working with chamber filter press, you have a lot of manual labor where you have to open and close the chamber filter press. While with this centrifugation unit, you can work in a continuous manner and work in essence more efficiently. Similarly to chamber filter press filtration, there will always be a little bit of pellet left or a little bit of cells left in your supernatant, so you do need further polishing to remove this pellet. Here I want to show you some pictures of how this looks in the feed on the left, and then the clarified supernatant on the right. So you can very clearly see in a single pass how much of the cells are effectively removed. And then coming to the results, here we obtained, so the recoveries are somewhat lower than with chamber filter press filtration, So in a single pass, we obtained 53%, but you can see with one additional wash, we were able to increase the recovery up to 78%. In this case, we decided not to continue performing additional washes, but you can see that with 2 or 3 additional washes, you can also increase your recovery by up to more than 90%. After polishing, in our case, we had then a 77% recovery of the enzyme. The lower recovery here is partially explained by the lower dry matter content of the slurry, because here you really still have a wet slurry, while with chamber filter press you do have this dry cakes. Then next one. So with this I want to summarize and come back to the comparison of the 3 different strategies that we have evaluated. In our case, with ceramic cross-flow microfiltration, we did have a low UPO12 recovery, which makes it less interesting to use this as a scale-up strategy for the process. Yet, for other enzymes, we have seen at our facility, or other proteins, that you can get very high recoveries, and then this becomes a very interesting strategy to work with, because it's also very easily scalable. Additional benefits are that this can be done in a very continuous operation. You don't need further polishing, and as I mentioned, biomass valorization is easily possible because you don't introduce any foreign bodies into your biomass. Going over filter press dead-end filtration, in our case we got a very high UPO12 recovery, but as drawbacks are that this is batch-wise and very labor intensive. Also, biomass valorization becomes more cumbersome because you are introducing these foreign bodies into the biomass. And then this tax centrifugation, the recovery here in our case was somewhat intermediate, but this could be improved by adding additional washes. And of course, continuous operation is possible. And similarly to cross-flow microfiltration, biomass valorization is quite easy to achieve. However, a polishing step is still required. So then I briefly want to introduce the Biobase Europe pilot plan. So this is the facility where we did all these scale-up tests. We are certified to also produce food-grade products. So, for example, food-grade enzymes. Then you can press next a couple of times. So this is just to show a bit the division of our hall. So we have a big hall for biomass pretreatment, also for purification, but also for biocatalysis reactions. And then another hall for larger scale, so more than 10 tons of DSP processing. Then next. Of course, our laboratory where we do a lot of fermentation and DSP development before doing scale-up. And then our fermentation halls with fermenters up to 15,000 liters, but then our latest installation, the 75 cube, which should be operational by the end of this year. Finally, we also have a green chemistry hall where we can work with explosive solvents, for example, with large volumes of methanol, which do require these additional safety precautions. And then the final place are the customer hubs. Okay. Coming back a bit to the topic of, so you can see the list of all the different equipments, different scales that we have, but I mainly want to highlight here the off-gas sensor, because coming back to the Industry 4.0 discussion that was held yesterday, and I think the very nice work by the group of Chavi, working on, for example, this RQ-based control, and with tools like this, we can really allow this continuous monitoring and these process analytical technologies to really go to the next step into the bioeconomy. Then here you can see the pictures of the 15 cube and then the 75 cubic fermenter that will be operational at the end of the year. Here I just want to highlight one thing. So we are a very modal facility. where we have different equipment really ranging from different scales. So for example, for the lab, you can see the unit that we have used for the development here. And then for every times 10 increase in scale, we do have similar equipment that can really show the scalability of this equipment. Then I was also a bit inspired by the talk from Dieter Matanovic, because now there's also the possibility to use CO2 working with Pichia, especially in the framework of global warming and the carbon capture and utilization framework. We have been investing heavily as well into gas fermentation, where we have several pressure-resistant reactors that can go up to 10 bars. And I think more what I want to highlight here is that we also have a mobile pilot plant where we can actually bring the equipment to the gas source, which is quite interesting because gases are more difficult to transport than, for example, a solid or a liquid medium component such as glycerol or methanol. Yeah. And then finally, I want to thank everyone involved, especially Nuria for the nice collaboration. So you can see the two of us, they're happy with all of the products, all of the concentrated enzyme that we produced. I also want to thank the group of Busy, and especially Tony Glieder and then Chabi from Huawei, and all of the colleagues at the Biobase Euro pilot plant. And thank you for your attention.
I have one for the ceramic filtration. Do you need to dilute the Pichia broth, or do you go in with an undiluted?
We can go undiluted into this. So there's of course a certain limit that you can go to, but in this case we could work undiluted. Yeah.
Thanks for your talk, Peter. So you had 4 criteria to pick your step to remove your biomass. Which one is the most important in your mind to look at?
Yeah, it's a good question. And I think, of course, the recovery is the most important one. If you have a recovery of let's say 5%, you can have a very easy and continuously operatable process. But if your recovery is 5%, it's not going to do a lot. So I would put the recovery as the primary criteria in this case. The others, for example, biomass valorization, it's a very nice to have. Also in the current climate where we're really going towards a circular economy and really trying to work on biomass or waste stream valorization. It's a very nice to have, and I think for sure something that we should look into, but yeah, not the priority in this case.
So which recommendation did you make for your client?
The recovery of the enzyme.
Okay.
Yeah.